Welcome to Chemistry 112. We will start today by continue looking at some of the old tests. And if we can get to it, we'll start chapter 14. I have recently sent you all a take-home test. Take-home test, advantage, disadvantage. Disadvantage, not multiple choice. Advantage, sure, it's a week long. You can. All I want is turn it into me in some form or another by the end of next Tuesday. So you got a whole week to work on that. Not online. Obviously, the time limit is 1 week. It needs to be either a separate document, separate sheet of paper. I put it as a PDF and send it to you. That should make it so you can see the equations. But keep in mind, you can access all the equations. The main thing is I can answer clarification questions, but you can't go to any teacher for help. That's the main thing. Make sure you show your work if there's a math problem, because there's partial credit. Make sure you explain your reasoning. Make sure you use your own words. Explain if you're going to use a thing offline, like a quotation or a definition out of this, just rephrase it in your own words. That's all I ask. Try not to be, if you're working with someone, try to use your own words. Don't just copy the word for word what your neighbor's saying. I'm not saying you can't work with other people, but make sure you answering the same questions. Make sure your numbers are the same. Maybe more than one version of the test out there that's very similar. Very similar. So you could still be doing the same concept of, say, freezing point depression and molality. But if you have 50 grams of this solute and they have 75 grams of the solute, obviously you're not going to get the exact same numbers. You could still be using the same equation, but you can't just copy the numbers. So make sure the point of this is not to kill anyone here. The point is, hopefully if you have to do this, you're going to maybe learn something. You're not just going to cram and slam it out and guess a bunch. You have some time to actually work it through and actually understand the concepts. So even if person A is working with person B and they have the different tests, if you can explain the concept, you both can get the answer. But okay. So we'll finish looking at the last year's test and look at last year's take home as well. Okay, nope, not that. There we go. Okay, we were in the middle of last year's test. 20. We just finished question 9. Question 10. A very easy problem if you know what to do, kind of tricky if you don't. Given similar concentrations of the following aqueous solutions, what solution would have the lowest freezing point? So aqueous, they're all in water. So the main thing here is what is dissolved. Molality, if molality is the same, the only thing that differs is the degree of ionization, meaning if they all have a Van't Hoff factor of 1, they would all have the same freezing point. That's the beauty of colligative properties. You don't care what is dissolved, you care how much of something is dissolved. So if they're all at the same concentration, the only thing that can differ is the Van't Hoff factor. Remember, or nonmetals bound to other nonmetals typically don't break apart in water. So the sugar in the top left corner, A, it may have a lot of atoms in there, but the Van't Hoff factor would be essentially 1. We don't care about the charges. So NaCl, 1 and 1, so that would produce 2 atoms. MgO, 2 and 2, but still 2 plus and 2 minus still only produce 2 atoms. It's CaCl2, which produces 3 atoms because you produce 1 calcium and 2 chlorides. So which one would have the lowest freezing point? It would be B. Which one would have the highest freezing point? A. Which one would be in the middle? C and D would be the same. But that's how we would approach that. Questions 11 and 12. Vodka contains 40% ethanol by volume, which means about 40 mils of ethanol, 0.789 grams per mil, and 60 mils of water, 1 gram per mil. What is the molality of vodka? And based on your molality from that problem, what is the freezing point of water if the freezing point depression is 1.86 of water? So in this case, so I'm going to pull up my document cam and we'll work this out. So there's a problem just like this on the test. Just like this, but not quite. Let's get this going. Okay, good, perfect. Throw that over there. Okay, and I need to go to doc. Okay. Okay, so with 40 mils of vodka, a density of 0.789 grams per mil would tell us give us the mass of ethanol, and the mass of and the molar mass of ethanol, which is C2H6O, 12 times 2 plus 16 plus 6 is 40. Wait, 3, yeah. It should be 46 grams per mole. So 1 mole, 46 grams. So I'm setting that up. This calculates the moles of vodka. The moles of ethanol in vodka. So 40 times 0.789 divided by 46. All that gives us how many moles? 0.686 moles. Now, water. The water is 60 mils with approximately 1 gram per 1 mil. Means we have about 60 grams of water. Real quick, do a quick math. 60 divided by 18, there would be 3.3 moles of water. So which one of these guys is in greater quantities? Well, it's obviously the water. There is 3 moles, approximately 3 1/3 mole, and 0.6 moles. Water is the solvent, so we don't have to worry about that. So molality says, we take the moles of our solute, 6 moles, divided by our kilograms of solvent. Since there's 60 grams, we're going to divide 60 grams by, and there's 1,000 grams in 1 kilogram. You get 0.06 kilograms. And so our first answer, it's a pretty big number, is 11.4 molau. 11.4 molau. So I'm jumping back to here real quick before we do the second part. We do the second part. Let's see. Oh, crap. Yeah. It's just want to make sure. Yeah. 11. So we have option 0.171, 0.686, 11.4. So answer C or D, 18.4. So the answer is C. Now, using that number, what is the freezing point depression of water? Freezing point depression of water. So going back to this. Back up. We have 11. The freezing point depression, delta T, equals negative I KF M. Ethanol, mostly organic, so I is 1. So negative 1 times 1.86, which is the KF I give you, times 11.4. 11.4 times 1.86 means we have a decrease of negative 21.2 degrees. Because the freezing point of water is 0, the new freezing point of vodka is negative 21 degrees, which is pretty darn cold, which is why Russians can just shove their bottle of vodka out in the snow, chill it, don't have to worry about the liquor busting at all. As you increase the alcohol content, the freezing point is going to keep dropping and dropping and dropping until you get to the point where it's crazy cold. Okay. Now, of course, that assumes water is the solvent. Water is no longer a solvent, then you have a different freezing point, a different KF. We'll worry about that when it comes down to that. Going back. Here is a phase diagram problem. This one's a little hard to see. If I'm not mistaken, the temperature here is in Celsius and the pressure is in atmospheres. We'll make the assumption. One thing you must always check is what is the units. This will be the place where you can, this should be something that is incredibly easy as long as you can read a chart. The problem becomes, are you going to make a stupid error? Stupid error. So what phase iodine when it's 298 Kelvin and 1 atmosphere? So 298 Kelvin is 25 degrees C. So because this is in Celsius, it's not way over here close to 300. It's way over here. So 1 atmosphere, I think it's somewhere like, I can't really read the units, it's so dang small, but it should be in the solid range. Iodine is a solid at room temperature. And then at what point temperature does the triple point occur? You're just eyeballing it. So what you have here, the triple point, we don't see, but there would be a critical temperature where this stops off. We have in here solid phase, liquid phase, gas phase, and up here somewhere that we cannot see would be the supercritical fluid. Supercritical fluid. Going to solid to liquid, we would have melting or fusion. Liquid to gas, we're looking at vaporization, condensation. Solid to gas, we'd be looking at sublimation and deposition. So anything that could be asked, what phase would it be at this point? Or what transition would it be at this point? You're just reading that, maybe moving it from the standard temperature and pressure to a certain point and seeing what happens. You're just essentially taking a starting point, drawing to a certain thing. So this shouldn't be a hard thing to do. You can easily look at your homework and practice from the homework before doing that on the test. What should be done to induce sublimation of iodine at 20 degrees C in 1 atmosphere? So if you're at 20 degrees C in 1 atmosphere, you would probably want to drop the pressure. Because if you increased the temperature, it'd go into the liquid phase. If you decrease the temperature, it'd stay solid. You increase the pressure, it stays solid, so you want to decrease the pressure, it goes straight down, goes from solid directly to liquid. What type of solid would you expect to be described as being held together by electrostatic attraction of localized charges? Simply put, that's ionic. Salt water contains approximately 35 grams of sodium chloride per 1 liter. If water temperature of the Caribbean is 27 degrees, what is the osmotic pressure of the ocean water? We'll go ahead and do that one real quick. We're almost done. This test, and then we'll look at the old test. The old take home. So, osmotic pressure. Osmotic pressure is pi I MRT. T is in Kelvin. R is our probably 0.08206, usually given. M is molarity. As we said, I just want to look at this. I want to look at this real quick. Sure. How many? We said 35 grams and 1 liter. 35. Okay. So we have sodium chloride, NaCl. So I is going to be 2. We have 35 grams. So to figure out the molarity, 35 grams, we have to figure out what is the molar mass. Sodium, look up on periodic table, 23. Chloride, 35.45. So the molar mass is about 58.45 grams in 1 mole. And the volume, we said, is 1 liter. So the molarity is 58. So M is 0.59, we'll say 599. Temperature, we say, is about 27 degrees. 27. We have to add 273. So that puts us clearly at 300 Kelvin. So to get osmotic pressure down here, we are going to say 2 times 0.599 times R times 300. If I specified this to be in bars, you would just have to use the 0.08314 instead of 8206. But it won't change the number by much. You do that math, the number you should get is about 29 and a half. 29 and a half as the pressure. So 29.5. Even if you'd used the wrong R, it would not have changed it by that much. So, that being said, last question before we get to bonus. What is the molecular formula of the crystal structure containing titanium, calcium, and oxygen? So oxygen is this the straight up normal looking shaded ones. The oxygens are on all of the edges. Looking at this cube, edge, edge, edge. Each edge is 1/4 of the cube. So each set of 4 edges adds up to 1 oxygen. Since there's 3 sets of edges, the top set, the bottom set, the middle set, that means there are 3 oxygens. The calcium is only in the dead center. It's only in the dead center. So there's 1 calcium. And the titanium is only in the 8 corners. Each corner is 1/8 of the box. So how many titaniums total? We have 1 titanium, 1 calcium, 3 oxygens. So it would be like CaTiO3, meaning the titanium would be a +4, the calcium would be a +2. 4 and 2 make 6. 3 oxygens make -6. So it's a perfectly balanced ionic compound. And the last thing was just kind of a property that we talked about, but like not that much. But I gave a hint. Complete the Rebus puzzle. What is a property of metal that can be drawn out into a wire? Well, what is that? It's supposed to be a duct. So what property of metals drawn onto wire? It's ductility, or a ductile. Ductile. So, but that was the test I gave last year. Now, I'd rather go over this one because this one actually is closer to what we will see. This one may be a little bit harder, maybe a couple more questions that are linked. I try to only have like 10 points per question. And each part of the question worth 5 points. So nothing's really more than. But okay, so looking at this, answer the following questions about interactions between the components in water. Methanol, CH3OH, sodium chloride, NaCl, propane, which is just C3H8, dimethyl ether, which is CH3OCH3, and chloroform CHCl3. So using dashed lines, show the interactions, draw the interaction between the component and water. Okay. Then label the strongest interaction type present in each interaction, either as ion dipole, hydrogen bonding, dipole dipole, dipole induced dipole, or London dispersion forces. So place the interactions in A to E in increasing interaction strength, and then D, which would experience the highest vapor pressure. So this one clearly has to be done from the dock cam. And this one, it's all the parts can be done kind of all at once. Okay. So let's look. So all these we have to look with water. So we draw CH3OH. We're looking at OH. Do an interaction with a water. Maybe another one. So what we have right there, we have hydrogen bonding. H bond. This would also have, this has H bond between itself. It has we would have dipole, and it would have LDF, London dispersion forces. Everything has London dispersion forces. London dispersion forces depend on the number of electrons and size. But which one's the most important? The H bond. Let's see, next structure is sodium chloride. Continue down. Na plus O. Dot. Maybe draw Cl minus. So this one's going to clearly be ion dipole. That sodium chloride can split into various ions. The negative is attracted to the positive hydrogens. The positive is attracted to the negative oxygens. Just putting the partial charges on there. I think the next one is propane. This is going to be not much of anything. Not really any. There's not really any attractions because this is all London dispersion forces. London dispersion forces. That's A, B, C. Let's see. Last two is dimethyl ether. Dot. This does have some hydrogen bonding. It would also have dipole. But please note, without the water, there can be no hydrogen bonding. Without the water, there can be no hydrogen bonding. Why? Because this one does not have an OH, an NH, or a FH. So if I just put this guy by itself, you can have a dipole with another guy. But it's not a hydrogen bond. Not a hydrogen bond. And the last one, chloroform. CH, Cl, D negative, D positive. We could have dipole. No hydrogen bonds. If I were to put these in order of increasing and decreasing, sodium chloride is number 1. Methanol is number 2, way up at the top, because hydrogen bonds where methanol can take a hydrogen bond and make a hydrogen bond. Then dimethyl ether would be number 3 because it can only take a hydrogen bond, but it can take one. Then chloroform would be number 4 in strength. And then propane would be number 5 in strength because it's only London dispersion forces. The final part of that question is, which one of these guys would have the highest vapor pressure? Got to remember, vapor pressure is dependent on a lack of interactions. Low interactions means high vapor pressure, means it will escape into the gas phase more easily. Which one of these would have the highest vapor pressure? Propane. It has the least forces. It only has London dispersion forces, so the forces are weaker, and thus, in fact, propane is a gas at most room temperatures. You pressurize it enough, yes, it will liquefy, but under most conditions, it is actually a gas. So yes, it's going to have a high vapor pressure. But how would you explain that? You would explain it has only London dispersion forces, and because London dispersion forces are particularly weak, it would be more readily able to escape into the gas phase. Question 2 this is a 2 or 3 parter. Based on the crystal structure, what is the ratio of black atoms to white atoms? If you don't already know, this is like a rock salt pattern. This is sodium chloride. The black atoms are in all 8 corners and all 6 faces. We count top face, bottom face, front face, back face, left face, right face. Each corner is 1/8, which makes 1 atom. Each face is 1/2. 6 faces, 3 atoms. So how many black atoms are we looking at? 4 black atoms. Now looking at the white atoms. The white atoms are in the edges. Each edge is a 4th. There are 12 edges, so 3 atoms. And there's 1 white atom right in the center, the body. The center body, the body at all. If it's fully within the cell is 1/2. Is 100% in the atom. So 3 plus 1, this is a 4-to-4 ratio, or 1-to-1. If this crystal structure represented a metallic solid, what type of alloy would it be? I'm not really asking this question on the test, but what type of alloy would this be? It would be like essentially a compound. It's it's like intermetallic compound or something like that because of the regularity of the pattern. Most of the alloys out there have just a random distribution of the replacement atoms. If an alloy has a regular pattern, it is actually a compound. It's like, as opposed to, replace 20% of the irons at random with this other atom. That's what makes some of the strange alloys. It's just an at random kind of thing. Well, compound has a regular pattern. Once again, C and D, we don't really need to do. I'll go ahead and show them real quick because we're here. So cubic close pack, using 2 different colors, complete the remaining layers of cubic close packed hexagonal structure. As I said, we didn't really go over this. Had you read the book, we might see this a little bit more, but so just draw the layers. So 1, 2, 3, I didn't really have the time, and it's not really easy to bring in the atoms. So essentially, we're essentially putting the atoms in the gaps. There's one. And in the special cubic close packed, we're then putting another one and a different gap. So there's three separate layers. There's three separate layers, each one not touching a different one. And then if you looked at that center layer, the center layer essentially touches six different atoms. I think I screwed up somewhere in there, but the center atom would touch 6 different atoms. But we're not going to worry about that. Not going to worry about that. There's nothing like that on the test. Hydrogen peroxide bottle contains 40% by mass hydrogen peroxide. Aqueous solution has a density of 1.15 grams per mil. What is the molarity? What is the molality? Then it says, what is the freezing point of the solution? And the solvent isn't hydrogen peroxide, it's water. And what is if the I for 1, what is osmotic pressure at 20 degrees? So we'll work out that real quick. Okay. 40% by mass means we have 40 grams of peroxide per 100 grams of solution, which would be times 100 to give it to 40%. To get molality is easy. Molality is moles of peroxide would be per kilograms. Moles per kilogram. So if there's 100 grams of solution, how much of that solution is water? 40 grams out of 100 means the water is 60 grams or 0.06 kilograms. Now I have to turn 40 grams into moles, no matter what. No matter what, for both problems, whether I'm solving for molality or molarity. Peroxide is H2O2, so 16 times 2 is 32, plus another 2 is 34. So the molar mass is 34 grams in 1 mole. So the moles are 1.1, we'll say 1.18 moles. So for molality, 1.18 divided by 0.06 kilograms is going to give us our molality. So all this is like this work right here would be a sufficient amount of work to show you understand how to do this. I show how I turned that. I show that I might want to show that 100 minus 40 is equal to 60. But I stated this, essentially the amount of water is 60. And then I showed how I got the moles divided by that. So that would be enough work to get full credit for the molality. The molarity. So the molarity is moles per liter solution. We already have the moles. Now we have to get the volume. We have 100 grams of solution. And we said the density of solution is 1.15 gram per 1 milliliter with 1,000 milliliters in 1 liter. So 100 divided by 1.15 divided by 1,000 gives us what? The volume is 0.08, we'll say 70 liters. So molarity is going to be 1.18 divided by 0.087. And the molarity is 13.6 M. So we have the molality, we have the molarity. We need the molarity to get osmotic pressure. We need molality to get freezing point depression. Freezing point depression. Freezing point depression, remember, is our delta T goes negative I KF M. I is going to be 1. We had 19.6. Yeah, 19.6. So the freezing point is low, negative 36.5 degrees. You had, in this problem, I gave you the hint, it's not water. You had to look up the freezing point. Oh, it's not peroxide. So you had to look up the freezing point of water. But that was given on a lot of different notes. A lot of different notes. So it was always there. The osmotic pressure is I times M, which is 13.6 as well, times R times T, which at 20 degrees is 293 Kelvin. I M R T. So 13.6 times 0.08206 times 293. Holy cow, that would produce 326, well, about 327 atmospheres of pressure. If you compare that to, if you put that adjacent to a like a pure water solution. So it's crazy. But so that is number 3, which was a four-parter. But each part, it's just conversion, another conversion, using the conversion, using the other conversion. So you still could have got 2 parts even if you couldn't do molality. Keep in mind, had I gotten the molality wrong and I used the wrong molality to get the freezing point depression, you would not have been penalized for that. You would have been penalized up here on part B for doing it wrong, but you wouldn't be penalized for part C for using your wrong number. Phase diagram for nitrogen. If the pressure were, notice this temperature in Kelvin here. Temperature in Kelvin. If the pressure was 100 atmospheres, what would be the temperature range in Celsius for liquid nitrogen? So 100. So if this is atmospheres, 100 is 10 squared. So liquid would be from about here to about there. So you'd have to estimate. That's, I think if I'm not mistaken, there's 5 dashes per every 100. 5 dashes means 20 degrees per dash. So you'd eyeball it. That I'd have to look. I can't really zoom in. You could zoom in. I'm not going to bother to zoom in, but you would eyeball it from here to here, turn that into Celsius. That'd be your answer. Crap. Okay. Then it's approximately what temperature and pressure would solid, liquid, and gas exist simultaneously? Where's the triple point? Eyeball it. Give me approximate number. You don't have to be exact, but you can get pretty close. If nitrogen would be cooled under vacuum from a stated atmospheric pressure conditions, every 20 degrees resulted from a decrease in pressure for half. What phase change would you first to occur? Where cooled under vacuum. So if we're from atmospheric to maybe a half. So where's STP? Every 20 degrees we drop, we're going to lose half of a atmosphere. So you're just trying to figure out, let's see. So we go from 1 atmosphere to a half. Then a half down to 2.5, and then from 2.5 to 1.25. And so that would be loss of 60 degrees. And then basically, if I'm not mistaken, you would, if you keep on going that pattern, you would eventually hit the your deposition. You would, that's an oddly worded one, probably not my best one, but it would, if you keep going at the diagonal down like that, you would probably hit here first. You go from gas to solid without passing through a liquid phase. Okay, number 5. Considering a 500-gram sample of aluminum nitrate dissolved in 500 grams of acetic acid, a polar organic solvent similar to water. What's the molality of this? The molality would be an increase in boiling point for acetic acid in that ionic aluminum nitrate solution. And then, based on your knowledge of solutions, do that. So let's just work through that through. What is molality? You would have to look up the KF of that, and that's something I don't have handy, but you could look that up. Given the fact that that this is a take-home test, you can look it up. Ideally, you have a book. In the book, you have in the book they have a series of KFs, so you can look those up. It would not be an issue. But without me pulling that up real quick, it's kind of beyond my scope. But okay. So looking at that 500 grams. So we can do this part just fine. We can do the molality because molality doesn't depend on the properties of the solvent. Molality is going to depend on, we have 500 grams of aluminum nitrate. So we're going to have to calculate what is the moles of aluminum nitrate. Aluminum is 27. Nitrogen is 14. There's 3 nitrogens. Oxygen is 16. There are 9 oxygens. So the molar mass of this is 213 grams and 1 mole. So how many moles do we have at 500 grams? We would have 2.35 moles. When we calculate molality, it's moles divided by kilograms of solvent. So how many kilograms? 0.4 kilograms. Kilograms. 5.87 molality for our first one. Freezing point depression, I, KF, M. Well, we have our KF, well, we have our M. If this acts, if acetic acid acts similar to water as a solvent, and this is ionic and will act as if the solvent is water, what would I be? We would form 1 aluminum and 3 nitrates. So I would be 4. I would be 4. Let's see if I can find this in an instant. If not, we just move on. Okay. See you guys. Hey, Nick. Okay, let's see. And point depression. Though, if you can't find it, I would suggest, honestly, Wikipedia works rather well for a lot of science stuff. Usually the numbers are reasonably good. Reasonably good. So acetic acid has a freezing point, T initial freezing at 16.6, and a KF of 3.9. So with that in mind, so 4 times 3.9 times 5.87. 0.9 times 5.87 times 4, going to be, we would drop in negative 91.58. Since the initial freezing point is 16.6, what does that mean? TF is going to be negative 91.58 plus 16.6. So the new freezing point is negative 74.97, or essentially negative 75 degrees. That's because TF minus TI is equal to negative 91 or 92 or 91.6. So since we have TI, we can find our TF. Now going back to the problem itself, there's a third part. Based on your knowledge of solutions and boiling point elevation. Oh, that crap. They wanted boiling point elevation. So that would have changed how I did this. Only that instead of negative I, you would have had positive I. Instead of that, you would have boiling. Instead of that, you would have the other number. So that's wrong, but right idea. Right idea. Same general process that you do with one. Based on your knowledge of solutions and boiling point elevation, what variables would following change affect? Changing the solution to 500 grams of gold oxide. Well, gold is a lot heavier. Let's see, I'm trying to remember what molar mass of gold. And it would split into less ions. So there's a good chance the molality goes down as well as the I would definitely go down to 2. So the boiling point elevation would decrease. Let's see, 196, 96 plus 16. Yeah. the molar mass is about the same. It's 212. So basically, the I has decreased from 4 to 2. So the boiling point of elevation would decrease by a factor of about 2. Changing the solute to sodium phosphate. Let's see, phosphorus is about 31 plus 16 times 3, 4 plus 23 times 3, 164. So the moles of sodium phosphate would have gone up. So even though the I was 4, I would still be 4. Even though the I would still be 4, the moles would have gone up, so the molality would have gone up, and so the boiling point elevation would have gone up. And the last one is changing the solvent from acetic acid to 400 grams of water. How would that have changed things? Well, what's that going to change? That's going to change the boiling point elevation value, the KB. And so because the KB changed, the boiling point would either go up or down comparing the two boiling point elevations. So that's how that would have changed it. Let's see, 6 is the last one. Considering the vapor pressure of acetone at 25 degrees, see the vapor pressure is 30.6 kilopascals. And at 0 degrees, vapor pressure is 9.39. So this is a Clausius-Clapeyron. 25, 30.6, and 0 degrees, we have 9.39. So what is the enthalpy of vaporization? And based on your calculation, what will be the vapor pressure at 40? Okay. So with that in mind, this last problem, then of course, what property of metal allows it to be shaped with concussive force? That's malleability. But, okay. Clausius-Clapeyron. Better or worse, it is ln P1 over P2 equals delta H over R 1 minus T1 over T2 minus 1 over T1. Trying to remember if that's quite right or not. Yeah, that's right. That's right. So this first one, it doesn't really matter which one we put into what blank, because we have the only value we don't have is this. We have to turn temperature into Kelvin for this to work. Otherwise, you'd be dividing by 0, which will not work. So ln 30.6 over 9.39 equals delta H. R is 8.314. That's P1, so that means 298. And that is 273. You have to go about solving this systematically. 1 over 273 minus 1 over 298 is a really small number. Divided by 8.314, also a really small number. ln of 30.6 divided by 9.39, really small number. But when I divide the answer from one side to the answer by the other side, you get, my energy here is 31961 joules. So I took this divided by all of this. I solved for my delta H. I said, if I retype that, ln 30.9 over 9.39, I'll type this into my calculator. Times 8.314 divided by 1 over 273 minus 1 over 298. Typing that in gives you this number. Now, with that in mind, we need to do this again with the new temperature of 40 degrees, which is 313. 313. So 1 over 313, it doesn't matter which temperature I use. You should get the same value. So I'll go ahead and use 298. That's fine. 298. We have to reuse our 31961 over 8.314 equals ln P1 over 30.6. So this time I need to fully evaluate this side. Fully evaluate this side before I take another step. 8.314 times 1 over 298 minus 1 over 313. And I get, this whole side gives me 0.618 to, I'll say 217. Goes ln P over 30.6. Here's where I have to do the inverse to both sides. So I take the second natural ln of my answer. And that gives me 1.8556. P over 30.6 is 1.8556. And then I have to multiply by 30.6. So what would my pressure be at 40 degrees? Pressure is 56.8 kilopascals. So I have to evaluate for the variable, which is why I chose P1 instead of P2 to be my variable I'm solving for. It's going to make my math a little bit easier. So that right there is example of what the test looks like. Similar, not quite the same, similar. So we'll go ahead and take a look at a few homework problems since we already have them up. So just show you what all we got. Okay, so we will actually look at some of these. Identify the solute, the better solvent, carbon, water, tetrachloride. This one's supposed to be just pretty easy. Pretty easy. You look at what properties they have, what are they going to dissolve. Carbon tetrachloride is a non-polar solvent. Water is a polar solvent. So anytime you have metal, non-metal, or something that can make dipole, you're going to have water. In the case of iodine or the organic, it's going to be the other one. Seriously. More soluble in hexane, less soluble in hexane, similar problem. Yeah, that one's not quite like, I'm not going to worry about that one. Yeah, solubility is not really on the test. Okay, here's a reasonable one. Using the gas solubility interactive and the solid solubility interactive, identify the effects of temperature on both solid and gas. So here's what we got to remember. When you increase temperature, most times you're breaking up the intermolecular forces. Breaking up the intermolecular forces by giving them more kinetic energy. So more often than not, when you increase the temperature of a solution, solids and liquids will dissolve better, but gases will dissolve worse because gases don't have many intermolecular forces in the first place. So when you increase the energy there, it's even easier to escape. So solubility of gas, you'll see a decrease in the solubility of gas, increase in the solubility of a solid on most times. But try the interactive, take a look. Okay. So, this is Henry's law. Henry's law simply states that there's a constant proportion of concentration and solubility. So 775 is the pressure. The pressure and concentration are proportional by a constant. So 775 times a constant equals 0.0347. So if the pressure changes from 775 to 2070, what would it be now? So you're simply looking at, you find the constant between the two, and then you multiply the constant by the new pressure. So for example, if the pressure had tripled, the concentration would have tripled. Solution is 2 grams of solute and 12.1 grams of solvent. What is the mass percent? Okay, this one's easy in one way, but a little tricky in the other. So 2 grams of solute, that's going to go on top. The mass of solution is 2 plus 12. So 14.1 grams of solution goes on bottom. So you'd say 2 divided by 14 times 100 would give you your mass percent. Because solvent plus solute equals solution. That one in itself shouldn't be too hard. Calculate the molality of this. So you turn grams of ammonium chloride to moles. You divide by kilograms of water. I'm not going to bother to solve that one out. Mole fraction. Mole fraction is the moles of A times the moles of B. Let's see. Okay, let's see if I can find one that we haven't really gone over. Here we go. The vapor pressure. We'll do this one real quick, and this will probably be where we end it. So biphenyl, C12H10 is a non-volatile, non-ionizing solute, and soluble in benzene, C6H6. The vapor pressure of pure benzene is 100.84. What is the vapor pressure solution made from dissolving 20 grams of biphenyl and 34 grams of benzene? This is Raoult's law, that pressure equals X of the solution of solve times your P star or P naught. So our P naught is, they say, 100.84. They say we have 20 grams of biphenyl of C12H10, and we have 34.6 grams of C6H6. So let me pull this up. .cam. Okay. So start. How many moles of biphenyl do we have? 12 times 12 is 144. Plus 10 is 154. How many moles of biphenyl do we have? Right, 154 is 0.1299. 34.6 grams, C6H6, times 12 is 72, plus another 6 is 78. 78 grams, 1 mole. 1.6 divided by 78 is 0.44. We'll say 36 moles. Mole fraction is going to be our moles of solvent, 4436, divided by, well, the mole fraction of solvent is moles of solvent divided by total moles. So add a 0.1299 onto that. You have 0.573. So 5735. So our mole fraction is 0.4436 divided by 0.5735. Fraction is 0.7735. That is the fraction out of 100%. The fraction out of 1 that the solvent contains. So if I did the mole fraction of the solute, 1 minus that would give us that answer. 1 minus that. So mole fraction 0.7735 times 100.84 would give us, this is the vapor pressure of benzene now. The vapor pressure has dropped to, we'll just say 78, because it's 77.999. So it is 78. There's our answer. Bar, whatever, it's Tor. Now, if biphenyl was volatile, then we would do the same with biphenyl. If biphenyl was volatile, then we would say, oh, so the mole fraction of there would be 0.2265 times its P star. And that would give us number. But that would be for biphenyl. But biphenyl is non-volatile. So we don't have to worry about that. So long story short, there, we're done. That's as far as we're going today. The test is due next Tuesday. Get it to me. Show your work. Read all the instructions at the top of the test. I'm not saying you can't work with other people, but make sure you're answering your questions. Make sure you're doing it. Show the work. The whole point of this is actually to learn the material, prove you can understand the material. If this is a total disaster, well, we can probably go back to something else. But for right now, we're going to at least try this as an alternative to just spamming Sun online, where some people who are good at multiple choice will do fine. People who are bad are going to bomb horribly. It's pretty much, Sun, the amount of work you put into it is going to show your grade, and not just like, oh, crap. It's completely something new. So, okay. But I will see you guys on Thursday and in lab.